Have you ever had that feeling, you solve a really tough problem, you check the back of the book, you got the right answer, but deep down, you feel like you didn't really get it? Well, you are definitely not alone. It turns out this is a huge thing for physics students. Today, we're diving into this fascinating paradox, the surprising gap between just calculating an answer and truly, deeply understanding the physics behind it. So here's how we're going to break this down. First, we'll look at a classic physics puzzle. I'm calling it the bullet and the block. Then we'll cover the two big ideas you need to solve it. After that, we get to the heart of the mystery, the paradox researchers uncovered. We'll pinpoint exactly where the understanding falls apart, and finally, we'll talk about the crucial difference between just doing something and actually knowing it. All right, let's kick things off with a piece of equipment that's a total classic in physics labs everywhere, the ballistic pendulum. And get this, for a long time, this wasn't just for school. Police labs actually use this thing to figure out the speed of bullets.
Pretty cool, huh?
The whole setup is actually super simple. You've got a projectile, in this case it's a little ball, and you fire it into a bigger block that's just hanging there like a pendulum. The ball gets embedded inside and the whole thing swings up. The one single piece of information you need to record is how high it swings. The process itself is a piece of cake. You fire the ball, it gets caught in the block, and you just measure the final height of that swing. But here's the magic. From that one single measurement, you can work backwards and calculate the ball's initial speed. So how on earth does that work? Well, to solve this puzzle, students are taught to use two of the most powerful, most fundamental laws in all of physics. You can think of them as the essential tools you need for this job. On one side, you have the conservation of momentum. This is the rule that governs the collision itself. Basically, the total momentum of the ball and the block right before they smash into each other is the exact same as the total momentum right after. Then you have the conservation of energy, which describes the swing. The energy of motion, that's kinetic energy, gets turned into the energy of height or potential energy. But there is a catch. And this is the critical detail. This collision is what we call inelastic. When that ball slams into the block, a bunch of energy is lost. It makes a sound, it generates some heat. That's lost energy. So what that means is you can't use energy conservation for the crash itself, only momentum. You save the energy rule for after the collision to analyze the swing. This distinction is absolutely key. Okay, so we have a clear problem. We have two solid principles to solve it. You'd think that after years of practice, students would have this stuff down cold. But this is where our story takes a really unexpected turn. I mean, think about it. After years of physics classes, you would totally expect students to have a rock-solid grip on these ideas. They can do the math, they can solve for the velocity, so they must get it, right? Right? Well, as it turns out, that's not really the case. A big study from 2022 dropped a bit of a bombshell. It revealed that our traditional ways of teaching often don't help students build a real, functional understanding of the concepts. Students get really, really good at solving the problems on the test, but not so good at actually thinking like a physicist. So how did the researchers figure this out? They used a special tool called the Energy and Momentum Conceptual Survey, or EMCS for short. It's a multiple choice test, but it's really cleverly designed. It's not about crunching numbers. It's about probing whether you understand the concepts behind the equations. And oh man, the results were eye-opening. Just look at this. This chart shows how students did on one particularly tricky question. You can see that after their first physics course, only 29% of students got it right. But now look at the upper-level students. Their score is exactly the same, 29%. That's the paradox right there. Years of extra study, more advanced classes, and it made zero difference in their conceptual grasp of this problem. Wild, right? So what is going on here? Where is this understanding breaking down? Let's play detective for a minute and look at a couple of these questions from the survey that consistently seem to trip students up. So this is it, the infamous question 22. You've got three identical balls. They're all launched with the exact same initial speed, but in different directions. One goes straight up, one at 60 degrees, and one at 45 degrees. The question seems simple enough. Which one is moving the fastest when it crosses that dotted line on the way down? The common wrong answers tell you a lot about the flawed thinking. A lot of students pick ball 1 because they're zeroing in on its vertical motion. Others pick ball 3, and their reasoning is that gravity doesn't affect horizontal speed. In both cases, they're getting lost in the weeds. breaking the problem into components but totally missing the bigger picture. But here's the elegant solution. The trick is to just think in terms of energy. All three balls start with the same speed, right? That means they all have the same kinetic energy. And they all fall the same vertical distance, so they all have the same change in potential energy. So if you just apply the law of conservation of energy, they must all have the same final kinetic energy. And that means they all have the same final speed. It's that simple. No complicated trajectory math needed. Okay, let's look at case number 2. We've got a satellite in a perfect circle around the Earth. As it goes from point A over to point B, what can we say about the work being done on it by gravity? This is another one that causes all sorts of confusion. A really common mistake here is to say that the satellite's velocity is unchanged, but that's confusing speed with velocity. Its speed might be constant, but velocity includes direction. And because the satellite is constantly turning, its direction is constantly changing, which means its velocity is too. Another trap is thinking the potential energy changes, but in a circular orbit, its distance from Earth is always the same. The correct answer is that the work done by gravity is 0. Nothing. Why? Well, in physics, work is only done when a force pushes or pulls in the same direction something is moving. But here, gravity is pulling the satellite straight down toward the Earth, while the satellite is always moving sideways, at a right angle to that pull. The force and the motion are always perpendicular, so no work gets done. So when you put these examples together, they reveal this really fundamental split in how we learn things. It's the difference between just following a procedure and actually understanding a principle. On the one hand, you have what's called algorithmic problem solving. You can think of this like following a recipe. You see a problem, you match it to a formula you've memorized, you followed the steps, and you get a number. But on the other hand, you have functional understanding. This is when you know why the recipe works. You understand the concepts, which means you can adapt and apply them to brand new problems you've never seen before. And this quote from the study really just hits the nail on the head. Students can get incredibly good at recognizing problem types and just spitting out the solution they've memorized. But then you ask them a seemingly simpler question, one that requires real conceptual thinking, and they get stuck. They've learned the how, but they've completely missed the why. And that really leaves us with a final thought, and it goes way beyond physics. Think about your own life, your own learning. Where are you just following the steps? Where are you just matching patterns? And what would it take to go from just getting the right answer to truly, deeply understanding why it's right?